Hi everyone. In this lecture we're going to wrap up our chapter on amines and we're going to discuss the formation of diazonium salts and then also their reactions. But first let's just compare and contrast a couple of acids, one of which we're pretty familiar with at this point. So the first acid on the left is nitric acid, HNO3, and we have used this acid previously with sulfuric acid to produce the nitronium ion. And then we used the nitronium ion in reactions with benzene. So we would create, for instance, add a nitro group to our benzene ring. Now the acid on the right is nitrous acid, or HNO2. HNO2. And if we react this with sulfuric acid, we get something a little different called the nitrosonium ion. Now, this nitrosonium ion has a resonance structure. So on the first structure we drew here, nitrogen has a positive charge. But we could move electrons from oxygen down to create a triple bond. And that will neutralize nitrogen and create a positive charge on oxygen. So in the hybrid structure, nitrogen and oxygen have partial positive charges. Although the structure on the right is actually the major structure. So it's the major contributor to the hybrid structure. Now, today we're going to focus on nitrous acid and the nitrosonium ion because that's what's going to help us form our diazonium salt. So let's look at the mechanism for the formation of this nitrosonium ion. All right, so we're going to start with our acid, this nitrous acid, and we're going to react this with another stronger acid like sulfuric acid, or you could even use hydrochloric acid, just anything that's really strong. And what happens is the oxygen in the alcohol group there is going to protonate itself and create a good leaving group. So in the next step, oxygen is going to create a triple bond with nitrogen, which will kick out our leaving group. And that's how we end up with the nitrosonium ion. Oh, whoops, excuse me. Nitrogen is not positively charged here. Oxygen is. And of course, we also form water as a byproduct there. All right, so let's look at how the nitrosonium ion will react with a primary amine. So let's say that we have a primary amine, and we're going to react this with sodium nitrite, which is the conjugate base of nitrous acid. And we'll also add hydrochloric acid or sulfuric acid, either one works. So sodium nitrite and hydrochloric acid are going to form our nitrosonium ion. And we'll have a chloride ion hanging around to balance the charge. And now we can react this with our primary amine. So the primary amine can actually attack the nitrogen in our nitrosonium ion, because remember, in the hybrid structure, the nitrogen is partially positively charged. So what that gives us is a double bond to oxygen, and now we have a new bond to our amine. So next, remember that when we form the nitrosonium ion, we do also produce water. So the water molecule that is lost as a byproduct can actually deprotonate the positively charged nitrogen. Okay, so now in the next step, we're going to see yet another reaction with acid. So the oxygen on top is going to grab that proton from our acid and protonate itself. And then in the next step, we'll see another reaction with water, where water is going to deprotonate our nitrogen again. Excuse me, this is actually going to create a double bond between the two nitrogens, and then we'll move electrons up to oxygen. So now we have an alcohol on the top here. And we're just going to react this with water one more time so that we create a good leaving group. And in the last step, that nitrogen connected to the alkyl group is going to create a triple bond, and our leaving group will leave. So now we have a triple bond between the two nitrogens, and we have an alkyl group as well. So this is our diazonium salt. I should have left myself a little more room. It's hard to fit everything onto one slide sometimes. The nitrogen in the middle will be positively charged since it is bonded to 4 different things, and the nitrogen on top will be neutral. Okay, so let's look at what happens if we try to perform the same reaction with a secondary amine. All right, so we'll react our secondary amine with sodium nitrite and hydrochloric acid. So we end up forming that nitrosonium ion again with a chloride ion balancing the charge. And now we're going to react this with our secondary amine. So the nitrogen from our amine is going to attack the nitrogen in the nitrosonium ion, which will move electrons up to oxygen, just like we saw before. So now we have a double bond to oxygen, and we get the following. Again, similar to before, water is going to deprotonate the positively charged nitrogen, and we're going to end up with something called N-nitrosamine, because we no longer have any protons that we could continue to remove from that second nitrogen. So the reaction just kind of stops here. And N-nitrosamines are carcinogenic. There's actually some N-nitrosamine molecules in tobacco. So we want to try to avoid this type of molecule. So when we're doing these diazonium salt reactions, we have to use a primary amine. Okay, so let's look at an alkyl diazonium salt. So let's say we formed, let's say we're using this primary amine here, and we're going to react this with sodium nitrite and hydrochloric acid. what do you expect our product to look like? And you can pause the video to try to figure out what that product would look like. Okay, so what we should end up with is our diazonium salt. So that nitrogen, or that N2 group, is going to replace our amine, or take the place of the amine, or however you want to say that. And then a chloride ion will be hanging around to balance the charge. Now, this is super unstable. And the reason for that is nitrogen gas could form, which could build up pressure. Now, this could be useful in some instances. So, for example, we could end up with a carbocation and nitrogen gas, which the carbocation could then go on to do other chemistry, so that could be useful. But let's look at something that's a little more stable. So let's look at aryl diazonium salts. So an aryl diazonium salt has some sort of aromatic group attached to our N2 there. And we could do a lot of chemistry here. But first, before we talk about the type of chemistry we could do here, let's think about how we would form that diazonium salt. So what would we have had before the diazonium salt? An amine, right? So we probably would have had aniline, and then we can just react that with sodium nitrite and hydrochloric acid to get our diazonium salt. But in order to have an amine on your benzene ring, what do you have to start with? A nitro group. So how do we turn a nitro group into an amino group? We have to perform a reduction. And what are the reducing agents we would use here? Well, you could use zinc and hydrochloric acid, or iron and hydrochloric acid. So that's kind of our synthesis pathway there. And of course, you could go a step back and start with benzene and nitric acid with sulfuric acid. But let's focus on some of the reactions that we can perform with this diazonium salt. So there are a lot of different copper-containing reagents we could use, like copper 1 chloride. And this is actually going to replace our N2 group with a chlorine. You could also do the same thing with copper 1 bromide, and that would replace the N2 group with bromine. You could keep going. Copper iodide will replace the N2 group with an iodine atom. Copper 1 cyanide will also do something similar here, where you replace that N2 group with a cyano group. So all of these reactions are called Sandmeyer reactions. So these are super useful. Let's look at a couple of other variations of this type of reaction. So instead of using a copper-based reagent, we could use, for instance, water and heat. Do you have any guesses on what we'll end up with? Phenol. So we'll replace that N2 group with OH. Another reaction we could do is, let's say we have our Sandmeyer, or our diazonium salt, and we're going to react this with something called hypophosphorus acid, H3PO2. this is going to replace the N2 group with a hydrogen. So we can just reduce that N2 group to a simple hydrogen. So these are very, very useful reactions that we can do. Okay, let's do a practice problem using everything that we just learned. Oh, here, let me add a slide. I think I'm missing a slide here. Oops. Oh, yep, I'm missing a slide. New slide. We'll call this practice. Okay, so in this practice problem, we're going to start with a benzene ring. And we want to try to add bromine around the ring, but they're all meta to each other. So see if you can figure out how to create this product on your own first. So you can pause the video and then we'll go over it together. All right, so previously we did see that if you have, for instance, an amino group on your benzene ring, the benzene ring will be super activated. So if you try to add bromine to the ring, you actually end up adding bromine to all of the ortho and para positions. So we could start by creating aniline with that amino group there, and then add bromine. Okay, so how do we create aniline? Well, before we have our NH2 group, we have to add NO2 and then reduce it. So we'll use nitric acid and sulfuric acid. So that will add NO2. And then we'll reduce it using zinc and hydrochloric acid. Okay, so now we have aniline. And then we'll add Br2 and iron tribromide. And we'll add it in excess just to make sure that we're going to add bromine everywhere, or at least to the ortho and para positions. Now, remember, if you want to prevent adding bromine to all of the ortho and para positions, you can acylate your amino group first, and then bromine will just add to the para position. So remember that, that's important, but not for this reaction. We actually want everything to be brominated. Okay, so we've got all our bromines there. Okay, now we have to figure out how do we get rid of that NH2 group? Well, remember on the last slide, oh, I deleted my drawings. Well, on the last slide, we had a diazonium salt and we reacted it with the hypophosphorus acid, which just replaced the diazonium salt group with a hydrogen. So what we probably want to do here is we're going to turn our NH2 group into a diazonium salt. So we'll use sodium nitrite and hydrochloric acid. All right, and we still got our bromines. And then in the last step, we can replace that N2 group with a hydrogen by using hypophosphorus acid, H3PO2. Okay, so again, remember, we have all of these new tools now that we can use to, for instance, just add a single bromine onto a ring, or a single chlorine, a single iodine, which remember, typically we don't, or we're not able to add iodine because it reacts too slowly. But if we create a diazonium salt and then use copper 1 iodine, or iodide, then we can actually add iodide to our benzene ring. So there's a lot of different useful tools here that we can use now. All right, so that's it for the amines chapter. If you do have any questions, please feel free to message me or set up an office hour.